Welcome to FLUIDOMOS. The FLUIDOMOS project aims to create a use case that extends the DELIS version 2.0 platform, conceived as a seamless, reconfigurable, and expandable home/building automation platform, to the FLUIDOS computing continuum environment. The Vemar Building Automation Facility serves as the pilot site for the FLUIDOMOS project, demonstrating the capabilities and benefits of integrating FLUIDOS into automation systems. This schematic showcases the building facade, enriched with the advanced automation features integrated within the Vemar headquarters. The system combines innovative technologies such as energy management, light control, video surveillance, and environmental monitoring to create a fully automated and interconnected environment. The project demonstrates how FLUIDOMOS successfully merges multiple heterogeneous technologies to enhance efficiency, security, and sustainability. Through this cutting-edge implementation, the Vemar site serves as a benchmark for the future of smart building automation. Giving an overview of the pilot site, here is an aerial view of the building's location, highlighting its position within the urban context. Then images display two perspectives of the building's facade, showcasing the modern architecture and design of the pilot site for the FLUIDOMOS project. A closer look at the pilot site building shows the main entrances, highlighting accessibility and modern design, the various functional spaces within the building, including a conference room, a reception area, and dedicated workstations. Together, they illustrate how the site is structured and used for FLUIDOMOS project's activities and objectives. The diagram illustrates the architectural structure of the DELIS system, showcasing its two main environments. On the left, the diagram illustrates the architectural structure of the DELIS system, showcasing its two main environments. The DELIS platform employs Ruby-based components, including user interfaces, API RESTful services, and a database for local processing. On the right, the DELIS platform integrates Python-based frameworks and plugins for advanced web services and actions, managed through edge controllers connected to sensor networks. The second diagram provides a detailed representation of the FLUIDOMOS architecture. It highlights the cloud-based infrastructure, which relies on a PostgreSQL and MongoDB database, and connects to edge clusters for localized operations. Each edge cluster serves multiple areas, hosting controllers, and nodes to process data from IoT devices and manage system resources. Together, these diagrams depict how DELIS becomes FLUIDOMOS through the use of FLUIDOS, delivering scalable and efficient building automation solutions. This diagram depicts the architecture and flow of components within the FLUIDOMOS system. At the center of operations is the Consumer 1 FLUIDOMOS control plane, which manages interactions with multiple entities. The Worker 1 FLUIDOMOS node is linked to a virtual private server, VPS, facilitating remote operations. Similarly, the Sedge 1 FLUIDOMOS node connects to Edge 01, which interacts directly with a sensor set labeled Sensor Set 01, enabling real-time data collection and processing at the edge. In parallel, the diagram shows the LICO FLUIDOS provider, which represents the virtual node acting as the FLUIDOS peer. This node links to the Provider 1 FLUIDOMOS control plane and Worker 1 FLUIDOMOS, which also connects to the VPS. Key features such as FLUIDOS peer, namespace offload, and affinity rules enable system functionalities like workload distribution, namespace isolation, and optimized resource affinity across these interconnected nodes. Together, this structure ensures efficient coordination between cloud, edge, and sensor layers within the FLUIDOMOS ecosystem. This is a photo of the Revolution Pi hardware, commonly usable for edge computing. The device is mounted on a DIN rail and connected to multiple expansion modules. Various cables are attached, providing power and communication between components. This screenshot shows the control plane of the cluster Consumer 1 FLUIDOMOS, where the edge node is successfully connected. The table displays system details, including internal and external IP addresses, the operating system version, and the running container environment. Another screenshot, taken from the edge device, confirms its connection to the cluster via the F0 network interface. The network configuration and assigned IP addresses are visible, verifying proper communication. The final screenshot, also from the edge device, shows the status of the agent service. The service is enabled and actively running, ensuring the device is properly integrated within the cluster. Logs indicate that the agent successfully started and is communicating as expected. This YAML file describes a Kubernetes deployment configuration. The replicas field specifies that 4 identical pods of the application named cable should be deployed. This ensures scalability and redundancy, allowing the system to handle more traffic and provide fault tolerance in case of pod failures. In the affinity section, specifically under node affinity, rules are defined to control where these pods can be scheduled. These values indicate that the pods will only be scheduled on nodes whose hostname matches either FLUIDOS provider or Quarker1 FLUIDOMOS. This setup ensures that workloads are directed to specific nodes, optimizing resource usage and ensuring proper placement within the cluster. In summary, the configuration balances scalability through replicas and targeted scheduling via affinity rules, enhancing both performance and reliability. Following images contain terminal outputs of commands executed on FLUIDOMOS system using Lico, a platform for dynamic and transparent Kubernetes cluster federation. The outputs display the status of the Lico control plane and a peering session established between the two clusters of the system. The image showcases a system setup, where FLUIDOS consumer is connected to FLUIDOS provider, successfully establishing network, API server, and resource sharing functionalities. All key Lico control plane components are running correctly, and the connection has low latency, 30 milliseconds, with a significant resource pool available for scheduling workloads. The following example demonstrates how services are migrated within the FLUIDOS environment from one cluster to another, simulating the complete failure of the provider cluster. In the current screen at the top, a CLI is visible, displaying the pods running on the nodes of our system. This shell is open on the consumer control plane, where it detects the nodes consumer1 FLUIDOMOS, Quarker1 FLUIDOMOS, Sedge1 FLUIDOMOS, and Lico FLUIDOS provider, the latter representing the provider cluster. At the bottom right, a CLI shows the nodes connected to the control plane. At the bottom left, a browser window contains 2 tabs. The first tab displays the response times of FLUIDOS services. These response times reflect the execution of pods within the remote cluster and, therefore, account for network latency. The second tab provides access to the Proxmox control panel, allowing various operations on managed virtual machines. At this point, we simulate a provider failure by shutting down the 2 virtual machines that compose it. The Lico FLUIDOS provider node transitions to the not ready state, and response times decrease. This indicates that services have migrated from remote execution on the provider cluster to local execution on the consumer cluster. Although the system still detects running pods on the provider, they are no longer reachable, as shown by packet loss in the ping output. By manually removing the unreachable pods, the system is cleaned up, reflecting a scenario without the provider. Finally, restarting the provider's virtual machines and waiting a few minutes allows the provider's nodes to reload. Removing the excess pods on Quarker 1 restores the system to its original state. Thank you so much for watching this video. We truly appreciate your time and interest in our project. We hope you found it informative and engaging. If you enjoyed it, feel free to share or leave a comment. We'd love to hear your thoughts. And if you have any questions, don't hesitate to reach out. Once again, a huge thank you for being here. Stay tuned for more, and we hope to see you again soon.